Hello friends, you are welcome to the Jamb41's YouTube channel. In this video lesson, we are going to give attention to a question sent by a registered Jamb41's student. Now this question is a radioactivity question. Now this is what I want us to do as we kick off dealing with this question. I'm going to use three different methods to solve this particular problem. Okay, then at the end of these, please, I will welcome your comment. You can drop your comment in the comment box stating which of the method you find interesting. Please do not forget to subscribe to my YouTube channel, like and share this video also and others to your friends and other scholars so that they can benefit from this YouTube channel. But don't forget, you too can join the Jamb41's special learning class. To do this, feel free to contact me and of course to get the necessary information on how to join this class. So we shall be going straight on to see what the question is about. 87.5% of a sample of pure iodine 131 decays in 24 days. What is the half-life of iodine 131? So like I rightly said, this question is a radioactivity problem. We are required to calculate, to determine, to find what the half-life of iodine 131 would be in 24 days, given that 87.5% of this iodine 131 decays in 24 days. Now the first approach we are going to use is that which likely may not require you to use calculator, but of course to be able to survive this you should have good knowledge of multiplication. I had already said this in some of my videos anyway, for basic level of learning like primary school pupils, encouraging them to take their multiplication table very seriously because this can help to improve their rate of calculation. Okay, so like the approach, the first method I am going to use here, which would be necessary for those going for Jamb, okay, you would have to have a good knowledge of multiplication and of course indices. So let us see how we trash that method, and we are going to see. Now what you would have to need first is to know the fraction of this sample. In the question we're given 87.5%, but take note that this 87.5% was the fraction of iodine 131 that decayed in 24 days. Now what do we do? Since 87.5% of this sample of pure iodine decayed in 24 days, we shall simply indicate 87.5% as a fraction of iodine that decays in that given day. So I'm going to use this fraction decayed, FD. Please, I'm using FD to represent fraction decay. Is that okay? Now, it was given in the question to be 87.5%. 87.5% is the same as 87.5 over 100. This is cool. So this is a fraction of iodine 131 that decays in 24 days. But did you know the fraction of any radioactive sample that decays in any given day has this formula? Fraction decayed equal to 1 minus 1/2. That's simply 1 minus 1 over 2 raised to power n. This is interesting. You want to know this formula, okay? Memorize it. The fraction of any sample decayed in any particular time frame is 1 minus 1/2 raised to power n, where of course our n is equal to t divided by t half. That n is equal to the time it took that fraction to decay divided by a special time called half-life. The half-life time is the time it takes for half of that sample to decay. So for example, if I tell you that the initial concentration or quantity of a substance is, said, 50. That's a 50 gram or whatever. And then I tell you that you should get me the time it will take for half of that sample to decay. I am interested in that time it will take for that 50 to reduce to 25. I hope you get that right, because half of 50 is 25. So what time will it take for 50 to become halved, which is 50 divided by 2? You get 25. That time is a special time when you are dealing with radioactive decay. And I want to state that radioactive decay is modeled according to first order equation. Don't worry, in method 3, you are going to see that equation. But for now, just know that this n, alright, this integer is t divided by t half, where t is the time it takes for any quantity of that sample to decay. And then t half is a special time, half-life, the time it takes for half of that guy to decay. Alright, having said this, we shall attack this question now by making use of this fraction decay formula. What we'll do is to calculate n. From n, we can now get t half, being that we know the time it took for 87.5% of that sample of pure iodine to decay. Substituting, this would imply that the fraction decay, which is 87.5 all over 100, will be equal to 1 minus 1 over 2 raised to the power n. Good. Now, we want to solve this. Remember I told you that this approach I'm going to use, this method, you can deal with it without using calculator, because you don't need any special function here. All you just need is your plus, minus, times, and divide, as the case might be. And for those going for Jamb, those sitting for Jamb, where you are given some funny calculator in the system, that calculator, I've said in one of my previous videos, it doesn't have special function. It just deals with plus, minus, times, and divide. In fact, in those days, we call it business calculator, because that's the calculator that business people use. You just buy something, they multiply, subtract, and add, or divide, as the case might be. So you need good knowledge of your multiplication table. That is a key factor. I can remember one of my boy, a wonderful kid, Caleb, coming up with that quote, okay, that multiplication is the boat you need if you want to cross the mathematics sea. And you're dealing with calculation. It's all about mathematics, even though this is a chemistry question and could also be a physics question. But the students who sent this sent it with respect to chemistry. And of course, the chemistry is coded in their school as ICH101. Okay? So we move on. I'm going to convert this numerator to a whole number. Since I have one decimal, I'm going to multiply the numerator and denominator by 10. If it is 2 decimals, I'll multiply by 100. So if it is 2 decimals, you're going to multiply by what? 1000. So here we have 1 decimal, so numerator and denominator multiplied by 10 is going to give us 875, then divided by 1000, and that is going to be equal to 1 minus 1/2 raised to the power of n. This implies that now we can reduce 875 by 1000. Okay, divide by 1000, we can reduce that with your multiplication knowledge. If you do not know the highest number that can reduce this, you could start gradually reducing and then be fast. 5 can divide through. If 5 goes into this, 1 time remainder 3, attach the 3 to 7, you get 37. 5 into 37 is 7 times remainder 2. Attach the 2 to this 5, you get 25. 5 divides 25 gives you 5. So that 5 dividing 875 will give us 175, You can be fast about that. But anyway, let's just move on straight. You can reduce this straight on and you get 7 over 8. And then that's going to be equal to 1 minus 1 over 2 raised to the power of n. Then we shall make this 1 over 2 to the power of n subject to the formula, since what we are calculating is together with it. Doing that, this 1 would have to, cross this way, or rather, you can move minus 1 over 2 raised to the power n to the left-hand side, while 7 over 8 we move to the right-hand side. So this will give us a concept of 1 over 2 to the power of n equal to, we have 1 minus 7 over 8. So if we find the LCM of this guy, this will give us 1 over 2 to the power of n equal to, working out the LCM of this is a whole number 1 minus a fraction. The fastest way to handle the LCM is using the denominator to multiply this. You get 8 times 1, which is 8, minus 7, which will give you 1 over 8. Now we can move on to break this down using the knowledge of indices. 1 over 8, that 8 is 2 raised to the power of 3. Are you getting me right? So I'm going to write this as 1 over 2 to the power of n equal to 1 over 2 raised to the power 3. And then I will convert this to negative index. Yeah, in indices we have negative index law, which converts to reciprocal. Are you following? This 1 over 2 and 1 over 2 raised to the power 3, both of them are in reciprocal form, changing to negative index. This over 2 here, this 2 has power 1 under, so it's going to become 2 raised to the power of minus 1, and then everything to the power of n, equal to, this term would be 2 to the power of minus 3. With good indices knowledge, I want to believe that you understand what has been done here. But, you know, if you're finding any concept of mathematics, you know, tough or confusing, you can always contact me, join our special learning classes, where we'll put you through on the concept of mathematics, physics, chemistry, of course English, and soon biology is going to kick off. Alright, now let us move on. With this, if you open up this power using power law of indices, minus 1 times 2, minus 1 times n rather, will give us 2 to the power of minus n, and that will be equal to 2 to the power of minus 3. And then because the bases are the same, 2, we can cancel out the bases. Cancelling that out, you have minus n equal to minus 3, and then you can multiply or divide through by minus 1. If you do that simply, this minus minus will cancel, that's the point. And when you cancel, you have that your n is equal to 3. But hey, don't forget, you're not calculating n. Do we even know what that n specifically represents? N is a time factor. But I've told you that that n is equal to t over t half, where this t is the time it takes for any quantity of the sample to decay. Like in this question, 87.5% of it to decay. So we know our T. We don't know our half-life, and that is what we are calculating. Half-life of iodine 131 under this condition of decay. So recalling that our n is equal to T over T half, and we know our T from the question, where T is equal to 24 days. The implication of this is our n is 3, fix that, and then t is 24 divided by t half. So it implies that t half will be equal to, you cross multiply, divide both sides by 3. So 3 is going to come under here, 24 over 3. In conclusion, therefore, our t half, the half-life of this decay process, is equal to 8 days. This is how we deal with this question using the first method here. Remember that I made use of what? Fraction decayed. Next, I'm going to use method 2, where in this case, I'm going to be using the fraction left, no longer fraction decayed. You see, if I give you a particular sample and I tell you that a quantity has decayed, something will be left. Is that not so? How can we make use of the fraction left to determine the half-life of this iodine 131 in this decay process? Interestingly, I want to show you something before we move on to method 2. Here we have that fraction decayed is equal to 1 minus 1 over 2 raised to the power of n. From basic mathematics, we usually learn, that if you add up all proper fractions, you're going to get 1. And even in other concepts of, O-level learning, advanced level, we know that sum of all fractions, in the case of proper fractions, is going to be equal to 1. Which means if you get a particular quantity to be 1 minus the other, there is a relationship there. If this is fraction decayed, being equal to 1 minus this whole term, the idea is that fraction decayed plus fraction left should be equal to 1. So if fraction decayed is now 1 minus this term, it simply means that this term, 1 over 2 raised to the power of n, is actually fraction remaining or fraction left. And with that, we can calculate our half-life from there. Watch out as I deal with method 2. In method 2, we are going to make use of the fraction left, or the fraction remaining after this 87.5% has decayed, alright? Now, remember that we are told that 87.5% of a sample of pure iodine 131 decays in 24 days. Whenever you are dealing with percentage, what should you know? Total percentage is equal to 1. And just in a similar way, where total or summation of all proper fractions is equal to 1, The same thing in the case of percentage. If you add up all percentage, is expected to give you 100. Of course, that's why percentage is usually expressed over 100. Am I communicating? I hope this is making sense to you. If you have any question, you can always use the comment box. Drop your questions and I'll be there to respond. Is that okay? Having said this, we know that the fraction decayed is 87.5. Now, out of 100, I am telling you that 87.5% has decayed. You can get the fraction left by simply doing 100 minus 87.5. Don't forget, percentage decayed plus percentage that will be left or remaining will be equal to 100. Therefore, permit me to use fraction left, FL, for fraction left. From here, it's going to be 100 minus 87.5, which will give us, okay, that should be 12.5%. I've explained why this is so. Now that I know my fraction left, okay, that's percentage fraction left. Of course, what I am going to do now is to use the formula for fraction left. This is in percentage, so if I'm converting it to fraction, it's going to be 12.5 over 100, just like we did for fraction decayed, 87.5 over 100. So let us do that quickly and see. But then you need to know the formula for fraction left when you are dealing with radioactivity. And once again, I'd like to state that this method 2, you don't need calculator for that. With your basic knowledge of arithmetics and plus, minus, divide, and times, you can deal with this because it doesn't need any special function, okay? So for those who are sitting for Jamb, you want to take note of this. Then if you find yourself in maybe a school, say maybe advanced level, okay, where you use calculator, maybe the third method awaits you, okay? The third method awaits you. All said and done, let's move on, please. Having this, I'm going to tell you to take note of this. Fraction left is equal to 1 over 2 raised to the power of n. I said this earlier, and you know what your n is already. N is equal to t over t half. We know our t, the time it took for this 87.5% to decay, which means that it is the same time that it will take for 12.5% to remain. Having said that, we can now substitute. Fraction left is 12.5. We are dividing it by 100. That's equal to 1 over 2 to the power of n, where n, of course, is t over t half. Converting this, I'm going to multiply the numerator and denominator by 10, since this is one decimal point. So this implies that 125 divided by 1000 is equal to 1/2 to the power of n. We can reduce this. Good enough. 125 can divide itself to give you 1 and divide 1000 to give you 8. But like I said, if you have challenge of knowing the HCF, that is the highest common factor that can reduce this, take your time but be fast. With good knowledge of multiplication, you can start by using the smallest number that can divide. 5 can do that and you move on. Guess with this, 5 can divide up to 3 times, okay? Reducing this 125 to 1 and then reducing this 1000 to 8. Okay, let us move on, please. We shall now have 1 over 8 equal to 1 over 2 to the power of n. Essentially, this is giving us a certain level in that method 1. Okay, there's one certain stage we had something like this, where I did 1 minus 7 over 8, you know. So, are you observing something with this method? Breaking this down further, this is 1 over 2 to the power of 3 using indices, and then 1 over 2 to the power of n. Essentially, we are doing the similar thing we did in method 1 from this stage. Two to the power of minus 3 equal to 2 to the power of minus 1 in brackets, then power n. I've applied negative index law to them. And then working this out, we have 2 to the power of minus 3 equal to 2 to the power of minus n. No, minus 1 times n will give us minus n. Power law of indices. If a base has 2 or more powers, just multiply the powers out. This point, simply cancel out this common base 2. And then we have that minus 3 is equal to minus n. And simply you can also cancel out the minus that you multiply through by negative 1 or divide through by minus 1. Okay, so doing this, we shall just simply get that n is equal to 3. Having obtained n to be equal to 3, once again recall that n is equal to t over t half, where of course our T is given to us in the question to be 24 days. So if we substitute that in place of n, we fix 3. That's equal to 24 divided by the half-life, T half, cross multiplying and dividing both sides by the coefficient of T half, which of course is going to be 3 here. We shall have that T half is equal to 24 over 3, which gives us 8 days. So what have you obtained here? The half-life for this decay process, given that 87.5% has decayed, and of course that will leave us with 12.5%. Going through the fraction left method, we shall obtain once again that the half-life is 8 days. And you would agree with me that this is the same answer we obtained from method 1. Alright, remember fraction left. The fraction left is simply 1 over 2 to the power of n, where that n is t over t half, that is half-life. We shall now move on to see how we can use method 3 to deal with this same question and see whether we can obtain 8 days again as our half-life. And of course, if we are able to succeed in that, that's going to be kudos. It means that you are well prepared, and of course, you've been taught the various methods you can use to solve this question. Please, let us move on to the third method. In this case, you will be needing calculator, so I urge you to get your calculator as you follow along. Is that okay? In this third method, I'd like to state that I look at this as more of a method for those in advanced level, talking about undergraduates, okay, university students. And of course, this question, like I said, was sent across by a GMAT 41 student in advanced level, okay? And so they can use this method because calculator comes in here. Calculator comes in here, and I guess to say that when this stuff is being taught at that advanced level, usually the method used in generating the formula used for calculating things about half-life, things about decay constant, K, and of course, other things like the concentration or quantity of the radioactive substance. The method used in obtaining the formula is an integral method. However, I am not going to show any integration process here. I will just give you the formula. Okay, I'm sorry about that, but I really don't have any need of dealing with the integration because this video lesson is not based on the integration to obtain the formula. Let us see what we do. Generally, for a decay process, I think I said that under method 1 before I actually started dealing with method 1, that radioactive problems, are you following, right? When it comes to radioactive decay equations, they are modeled according to first order equation. This is where differential equation comes into play, differentiation. And if you are given a differential equation, you resolve that, you get an integral value. The integral value now is the main function. And of course, if you apply that here, this is what we usually set out as the basis. That the rate at which a given quantity of any radioactive substance decays is directly proportional to the quantity of that radioactive substance that you have from the beginning. That is written mathematically as dn over dt to be equal to, okay, let me use the sign of proportionality, to be directly proportional to the original quantity left. With this dn dt is the rate of decay. Okay, maybe to some of us we may not understand this clearly, no problem. The formula is just what you need for now. And for full range of learning on how the equation is derived and stuff like that, remember, like I said, you can always join the GMAT 41's special learning classes. Just contact me and you get the necessary information on how to join the class. So with this, we are going to have dn over dt. I'm going to introduce equal to. This is going to give us a constant which I'm going to call k, and I'll multiply that k by n naught. Is that okay? So the rate of decay is now equal to k n naught. Now, whenever you're talking about decay is just like a death process. So there is a reduction. Are you following, right? For that reason, we usually introduce negative here. This negative is interpreted to mean that this quantity of the substance you have is reducing with time, is decaying with time. So if I come over here, I can transfer that minus to the right hand side and we have it here. Is that okay? Having said this, it is important for you to know that writing dn dt is a differential process. dy dx, d this, d that, okay? It's telling you the rate at which something changes with respect to the other. This n here is the quantity. It could be the percentage, the amount of iodine 131 or whatever radioactive substance you are dealing with that you have, which is decaying over some time, t, okay? And so once we establish this differential equation, all I have to do is separate variables. This k is called rate constant. It is a time constant quantity. Are you following, right? Then this n naught is the original amount, the initial quantity of that radioactive substance that is there for you, that is decaying. For example, in this case where we are talking about percentage, we say, okay, the original amount is 100%. The examiner can give you this question in terms of mass, in terms of atomic mass units. Are you following? In terms of, let us say, a given quantity in mass per unit time. They can use any unit of calculation for you. So this n is the original amount that you have in that substance. So if I choose to bring this n to what I call the parent, dn, because this is the n dt. This dn will be controlling anything about the amount of that substance that you have. Then dt will be controlling anything about time. To achieve this, I'll do a form of separation. Bring this n naught here, take this dt there. Since this k, I said, is a time factor, we call it the decay constant or rate constant. Is that okay? Doing that, we shall have dn over n naught equal to negative k dt. At this point, we are meant to do an integration. Are you following, right? And although, let me just show the integral concept. Integral dn all over n naught, you are integrating from the original amount that you have to the final quantity left, and that's going to be equal to negative k. I'll integrate this part, the t part, from 0 time, are you following, right, to any given time, like the one given to us here. I am not interested in this differentiation integration stuff. That's not the basis of this video lesson. I could have just jumped to the formula you need for this, but I'm just establishing this to help you, especially those in advanced level, not those at O level or Jamb. Are you getting me, right? You don't need all these concepts. For you, per se, the method 1 or 2, I think, is sufficient. But for those in advanced level, it's important you get to understand how this thing, came about. Because, of course, when your lecturers, examiners are teaching this concept at that advanced level, they will technically do this. Is that okay? And that means you should have good knowledge of differentiation and integration. So, I will just tell you that if you resolve this integration, what you are going to get is this. I'm sorry if I'm not showing that. But what you are going to get is going to be ln n minus ln n naught. That's NO. This means the ln, logarithm to base e. Ln is a mathematics function called log to the base e. That e is a special number. It's there in your calculator, I think log to base e. You can say that in your calculator, okay? And of course, not business calculator. Calculator with special functions. That is why those sitting for Jamb would have nothing to do with this method 3. So moving on, having integrated this part and then fixed up the lower and the upper limit, this is what you will get. And that's going to be equal to, the integral of this part will simply produce time times minus k for u, which is going to give us negative kt. Alright, so I think this is just enough. The most important thing is, this is the formula you need for your calculation. This n is the final amount, percentage or concentration that is left after a given time t. Like in this case, you have 24 days. Are you following? So that time will be 24. Now, what is the concentration left after that decay took place over 24 days? So that concentration left is the final concentration, and that is your what? N here. This N naught is the initial concentration, where you started from. Our question is based on percentage. So our initial concentration definitely is 100. I've explained that already in method 2. Total percentage is 100. So in our calculation here, the N naught is going to be 100. Okay? Then equal to negative kt. That k is called the rate constant. That is what we will calculate here. Once I know the rate constant k, I can use it to determine my half-life, T half. So follow along as I do that, please. This is the formula you need. This is the formula. Every other thing I was doing here was just to show you that this formula did not come from the blue. Alright? There is a basis for it. So we move on. Ln is logarithm to this e. So the property of logarithm applies to it also. So this is going to be ln n over n naught. Take note, if you have log of a number minus log of another number and they have the same basis, you pick one of the logs there's going to be the first number divided by the second number. In one of my recent maths video lessons where I solved problems on mathematics workbook for Unit 6 students, we had a question here that I treated on logarithm, explaining certain laws of logarithm. So I've applied it here. Okay, log A minus log B, as long as the logs are in the same base, it's going to be log A over B. This limb here is logarithm to this E, so they have the same basis. And that's going to be equal to negative KT. Now let us fix up our values. This is going to be lane, open bracket. This N, I told you, is the final concentration, the final amount, the final percentage that you have after some of that sample have decayed. Here, 87.5% decayed. So the final concentration or amount or percentage that will be left will be 100 minus 87.5. Let me show that. 100 minus 87.5. Now we're going to divide everything by the initial, the original concentration or amount or percentage. Now I'm going to be specific using percentage because our problem here in terms of the decay is linked to percentage. So this is going to be over 100 because 100 will be the initial percentage. Are you following, right? And then that's equal to negative K. Our time is 24. Now, if you work out this, you get lane 12.5 all over 100. That's equal to negative 24K. Please get your calculator now. Like I told you, let us evaluate lane 12.5 over 100. If you like, you can press 12.5 over 100, get it in decimal. That should be 0.125. However you want to do that. So I reach out for my lane key. It's there on your calculator. Now it's going to be 12.5 divided by 100. Okay, and this gave me negative 2.0794. I'm solving in 4 decimal places for good level of accuracy. Minus 24K. Calculating my K, therefore, this is going to be negative 2.0794 divided by 24. The value of our rate constant K is equal to, this is negative 24. The minus we cancel out already, you know. 2.0794 divided by 24. And so the calculator tells us that K, the rate constant, is going to be 0.0866. Please take note for first order rates of reaction or simply first order decay process, which I told you radioactivity is. Radioactive equations are first order differential equations. The rate constant unit is per second. Is what? Per second. Does that make sense? It's per second. Now that I've obtained the rate constant, it's now time for us to calculate the half-life, which the question asked us to find. And it is interesting to know that half-life time, that time called the half-life, can be derived from this guy. All we just have to do is change this T to half-life. Then we know that the final concentration that will be left when the time is already a half-life time. I said that already from method 1, that final concentration will be half of the initial, which means that N in that case will be N naught all over 2. If you use that concept, you can derive the half-life equation because we're not deriving anything. I'll just write the formula for you that you should recall our half-life T half is equal to 0.693 all over the rate constant. Whether you are in O level or advanced level, you would have seen this equation under radioactivity previously. So if this is the formula for half-life that connects to rate constant, all we just have to do, let me conclude the calculation here, is to substitute. Our half-life T half is now 0.693 all over our K, and K is 0.0866. So reach out to your calculator, let us divide this and obtain the value of our K. 0.693, we are dividing it by 0.0866. And the calculator tells us that the value is 8.0023. It's going to be in days. The unit is going to be in days since the time was given to us in days. Now this half-life can be approximated. To the nearest whole number, you see that the half-life will be 8 days. And this is the same as the first 2 methods. Like I said, this method 3 is purely for those in advanced level anyway. Well, it's been a wonderful one, and I want to believe that you enjoyed this video lesson. If you did, please hit the like button. And if you've not subscribed, kindly subscribe to my YouTube channel, please. At GMAT41, click the subscription button. Share this video lesson to your friends, to other scholars. They have a lot to benefit from GMAT41's channel. It's been a wonderful time having you, dear subscribers, with GMAT41. I so much appreciate. Thank you very much. Truly, I've not been releasing content on regular basis. It's due to a health challenge that I am facing, and I've said that in one of my previous videos already. But remember that GMAT41 is always there for you. Okay, I am doing all I can to be regularly on so as to supply you with content that you need. But please, do me good, support the GMAT41's academic movement. Subscribe to this channel. Share my video lessons. Your comments are gratefully appreciated. In any ways you think we can improve more on this channel, please feel free to share that with us too. Thank you very much, okay? Wish you all the best, and please continue to take your studies seriously. I hope to see you in my next video lesson.